Swayam Prabha. Digital India. Educated India.
So we know the formula for gamma in, right? Because gamma in is equal to S11. This we covered in the previous parts. Okay. Now, what was the condition for stability in terms of gammas? The condition was for all gamma s lesser than 1, this is the condition for stability, right? So now suppose this condition is satisfied, okay, then according to, if for this condition to be satisfied, this one, then we know the value of gamma in from this equation, right? So let us plug in this value in this equation. So what we then get is okay. Now this can be simplified to this equation. Now, the derivation is given in the book by Gonzalez. Please go through it. Now this is of the form where RL refers to this value and CL refers to this value. Now this is nothing but the equation of a circle whose center is at CL. So CL is a vector quantity, and radius, this is a scalar quantity of that circle, is given by capital RL. So this is the condition that has to be satisfied, okay, for, so if this value is lesser than 1, then the system is stable. If suppose this value is greater than 1, then the system is unstable, and the equality to 1, that is when this is equal to 1, that serves as a boundary to the stability, okay. And this equation that we have derived is nothing but this equality. So once again, let me make it clear. So gamma in lesser than 1 stable, gamma in greater than 1 unstable. So gamma in equal to 1 defines the locus of points on gamma L plane that is the boundary between values of ZL for which the two-port network is stable and those values of ZL for which the two-port network is unstable. Okay, and when we equate this to 1, we get this equation. Okay, so let me rewrite it. Implies S11 plus S12 gamma L S21 upon 1 minus S22 gamma L equal to 1, and this can be shown to be equivalent to gamma L minus S22 conjugate minus delta conjugate S11 upon S22 square minus delta square is equal to modulus S12 S21 upon S22 square minus delta square. Okay, and this is the equation of a circle. So this quantity we took as CL, which is a vector. CL is a vector quantity. It has both amplitude and phase. But this RL, which is given by this value, is a scalar. Okay then. So we have established the equation of a circle. By the way, this circle is called the output stability circle. Why this is called output stability circle, even though we started with gamma in, is because it describes the locus on the gamma L plane, which is the output impedance or the load impedance, not the output impedance, the load impedance, and that's why it's called output impedance stability circle. Now, in the same way that we obtain this circle by equating modulus gamma in equal to 1, as you by now have realized that in for two-port networks, there is always a dual expression for everything. So if we can equate gamma modulus gamma in equal to 1, we should have another analogous equation equating gamma out modulus equal to 1, and we shall study that, and that will be known as input stability circle. Okay. Okay. So So what is the significance of this input or output stability circle? Let us consider the gamma L plane. Let us consider the gamma L plane. So this is our gamma L plane. Say this is our unit circle of our Smith chart. So we are drawing the Smith chart on the gamma L plane. Okay. So the y-axis will be imaginary value of gamma L. The real value will be, x-axis will be real value of gamma L. Okay. This is the x equal to 1 constant reactance circle. This is x equal to -1 constant reactance circle. And now say we plot the output stability circle, something like this. So this is my output stability circle. Now in this output stability circle, what happens is, first of all, as we just derived, this boundary is nothing but gamma in is a function of gamma L equal to 1. This the center, recall that we, so if suppose this is the center CL, that is its magnitude of CL is equal to the distance from the origin, and the phase is equal to the angle subtended by this dotted line with the x-axis. Its radius is given by RL, which we, according to the expression that I just gave. So now the question is, which is the stable? Okay, first of all, we know that this red line, this red circle, defines the boundary between stability and instability. That is, gamma L values inside this red circle are either stable or unstable. We don't know. But if the gamma L values inside the circle are stable, then the gamma L values outside the circle are unstable, and vice versa. So either the inside of this circle is the stable region or unstable. It cannot be both. That's why, isn't it? That's why we say this red circle to be the boundary between stability and instability. The question now is, which is the stable region? The inside of this circle or outside of this circle? How do we do that? Now, to determine that, first of all, see that for stability, again, let me write down the condition that gamma in as a function of gamma L should be lesser than 1. Now, let us see what is gamma in at gamma L equal to 0. That is nothing but S11, right? Because if you go back to that expression for gamma in, recall that gamma in is equal to S11 plus S12 gamma L S21 upon 1 minus S22 gamma L. So when gamma L is equal to 0, gamma in is equal to S11. Okay. So if that is the value, no, so S11 at gamma L equal to 0, so gamma L equal to 0 will correspond to this point. So this gamma L equal to 0 will correspond to the origin. Okay. Now, suppose our circle is like this, okay, as we have shown. So in this case, the origin lies outside this red circle, isn't it? So at the origin, gamma in is equal to S11, and say the modulus of S11, which is a property of the two-port network, is lesser than 1. If that is the case, then this point, the origin, gamma L equal to 0, must be the stable point, isn't it? Because That's what, so because again I'm repeating the whole argument that I made. See, for stability we know that this condition must be satisfied. Okay, and what I am trying to do now is trying to find out the value of gamma in when gamma L equal to 0, and that I find is nothing but the modulus of S11. Now I check the value of S11. If S11 magnitude is lesser than 1, then that means this gamma L equal to 0 is the stable point, right? Because at gamma L equal to 0, modulus of gamma in is lesser than 1, magnitude modulus of gamma in is lesser than 1. Now if this origin is stable, then all points outside this red circle also must be stable, because this red circle defines the boundary between stability and instability. So since now here, since the origin is outside this red circle, it lies in the stable region, and therefore the inside of this circle must be the unstable region. Is that clear? Similarly, if suppose if S11 is lesser than 1, inside of red circle represents unstable region. Okay. Similarly, if suppose S11 magnitude is greater than 1, then it means at gamma L equal to 0, my modulus of gamma n is greater than 1, which means the origin is in the unstable region. And therefore, if the origin is in the unstable region, then every point outside this red circle must be in the unstable region. Therefore, the inside of this red circle must be the stable region. Okay. Now, there is one more problem here. The gamma L itself, recall, has to be lesser than 1. Okay. So that means I can consider only points which are within this unit circle. That is another further restriction. Okay. So let us say the case is that modulus of S11 is lesser than 1. Then this region outside the output stability circle represents the stable region. Okay. And I can consider only points which are within this unit circle, because if I go outside this unit circle, then this condition is violated. Okay, and I don't want that. So if modulus S11 is lesser than 0, then this green shaded region represents my stable region. Okay. On the other hand, if modulus S11 is greater than 1, okay, then what happens? Then the inside of this red circle is the stable region, but I cannot go outside the unit circle, so my stable region will be this shaded blue region. Is that clear? Is that clear? Now suppose I had the output stability circle in a different way. Instead of instead of you know, like, let me draw it. So once again, this is my unit circle of Smith chart. And this red line represents my output stability circle. But suppose now it is like this. So here again, and say my S11 magnitude, let me write here so that it's not, say, S11 magnitude is lesser than 1. In that case, what happens? If that is the case, then this point represents a stable region, which means that the inside of this red circle in this case is the stable region. So in this case, the stable region will be this one, this green shaded region, because outside this red circle we will have the unstable region and we cannot go outside this unit circle. Okay. On the other hand, if suppose S11 is greater than 1, then this point represents an unstable region. Therefore, the outside of this red circle will be the stable region, and in that case my stable region will be here. Okay, so this is how we determine whether the whether the system is, which point within the unit circle is stable and which point is unstable. Now this of course represents what is known as potentially unstable. Both the two cases that we just discussed, both this one and this one, they are both potentially unstable. Why? Because for some values of gamma L, this is stable, both the two cases, and for some values they are unstable. Okay. Now in the same way that we have, in the same way that we had this condition for output stability circle, I mentioned earlier that we can also have a similar case for the input stability circle. So for the input stability circle, the equation of the locus on the gamma S plane. Okay, so the input stability circle is on the gamma S plane. The locus of the boundary between the stable values of gamma S and unstable values of gamma S is given by this. So gamma out, recall, is given by S22 plus S12 gamma S S21 upon 1 minus S11 gamma S, and that is equal to 1, and this in turn can be simplified to so here this represents RS, the radius of the input stability circle. This represents CS, the center of the input stability circle. Okay, now you might ask me which one is more correct. Should I check the stability using the input stability circle or the output stability circle? See, the two conditions are different. Output stability circles gives you the values of gamma L for which the system is stable or unstable, whereas input stability circle gives you the values of gamma S for which the system is stable or unstable. Okay, So we can have a similar, just in the same way that we had a treatment for, for example, let's see, let me draw it. So suppose, if you draw the unit circle, okay, and suppose your input stability circle is given something like this, and say S22 magnitude is lesser than 1, then this implies that gamma out, gamma S equal to 0 modulus is lesser than 1. So in this case, this point, the origin, represents a stable point. Therefore, the outside of this circle is the stable region. Okay, so this green shaded region represents the stable region. Note that you can never exceed, in order to satisfy this condition, isn't it? This always has to be satisfied, because gamma S, this means that gamma S is a passive load, passive source impedance. It's not an active. Gamma S and gamma L always have to be passive. So in that case, this shaded green region represents the stable values of gamma S. Okay, so both the circles are necessary, to test. Each has a different purpose. The output stability circle tests the values of gamma L for which the two-port network is stable, whereas gamma S, the input stability circle, tests the values of gamma S for which the two-port network is stable. Okay, now suppose we have, say, okay, let us, now that we are, so here, just want to do this for completeness, this will be imaginary values of gamma S. This is real values of gamma S. Okay, suppose we have our input stability circles like this. So once again, this is our Smith chart. Okay, and say my input stability circle is like this, totally outside the unit circle. Then what? Then what is the situation? Suppose now we have S22 magnitude lesser than 1. Then again, this point, the origin, represents a stable point. Therefore, the inside of this circle is the unstable region. So the stable region is nothing but the entire unit circle, which basically is the condition for unconditional stability. It means that for any values of gamma S within the unit circle, that is, with any values of gamma S lying within the passive region, the system is stable. So this represents unconditional stability. Unconditional stability as far as gamma S is concerned. Similarly, if suppose for the output stability circle also we find a similar case, that for all values of gamma L the system is stable, then it represents unconditional stability for gamma L. And so if both the conditions, that is, the system is unconditionally stable for all values of gamma S and also unconditionally stable for all values of gamma L, then the system is unconditionally stable. That's it. On the other hand, if suppose S22 magnitude is greater than 1, then what happens? If S22 magnitude is greater than 1, then it basically means that no point within the unit circle is stable, and if suppose this is the situation we have, then it means that for S22 magnitude greater than 1, the system is always unstable. Okay, so that is the conclusion. Now we can graphically develop a condition. So the condition is that suppose magnitude of CS minus magnitude of RS, if this is greater than 1 for S22 lesser than 1. So what this means is you find the distance of the center of the input stability circle, okay, that is modulus of CS, and then subtract that from that the radius, which is the RS, okay. So the difference, if this difference between the distance of the center from the origin and the radius of this circle is greater than 1, then the system is unconditionally stable. Okay. And similarly, if we can have a similar condition for the output stability circle also. Okay. If this condition is satisfied, then also, so for all values of gamma L, the system will be stable. Okay. Now this one other case can arise, which is this one. Suppose this is the imaginary gamma S. Okay. Now here also, and then suppose S22 magnitude is lesser than 1, and so here also, so this is my input stability circle, this is my unit circle in the Smith chart. So here also, even though mod CS is equal to 0, since RS, the radius of the input stability circle, is greater than 1, so this also represents a unconditionally stable. Now here one thing I want to clarify, I have been using RS and small rs interchangeably, so they represent both the same thing. Similarly, RL and small rl I have also been using interchangeably. Okay. Okay, so these are the two conditions for unconditional stability. Now suppose one way that using the Stern stability criterion, which we discussed in the previous part, we can establish the values for which we can make a unstable system stable. So I'll just explain what I mean. Suppose we have say we have our Smith chart, something like this. This is our unit circle. Now suppose this is a constant resistance circle where the resistance is Ra. Okay. And suppose this is our input stability circle which just touches this circle. Okay, so this is gamma out gamma s equal to 1. Okay, and say this is a constant conductance circle. Okay, yeah, and say the value of conductance is 1 upon Rb, and say our output stability circle just touches this one. Okay, so then in this case this represents a potentially unstable. However, if we add a series impedance of Ra, suppose this was our two-port network. So this was the potentially unstable two-port network whose input and output stability circles are shown in this diagram. Now if we add a resistance Ra in series, okay, Rs corresponds to that constant resistance circle which just touches the input stability circle, then it can be shown that the system will be stable. And this comes from the Stern stability criteria. We call that K dash for this system with the series resistance will be given by now because of this additional resistance Ra, the K dash, okay, which was say K without Ra, say was lesser than 1. Now with this additional series resistance Ra, K dash will be greater than 1. Okay, so K is without Ra. So that's how from Stern stability criteria we can indeed verify that the system is will be more likely to be stable. Now the derivation why by adding Ra in series, how K dash will be greater than 1, that is quite long and beyond the scope of this course. Or we can also, instead of adding a series resistance at the input, okay, we can do this achieve the same thing by adding a shunt resistance having value Rb at the output. So in this case also the system will go from instability to stability, where 1 upon Rb is the constant conductance circle which just touches the output stability circle. Okay, so after only one of these two configurations is enough. Okay, I mean if you just add Ra in series at the input or Rb in shunt at the output, it's enough. So after adding this, what will happen is this same circle, these circles will become like this. These circles will shift out like this. So that's all I had for this final concluding part of lecture 8. So here we discussed the graphical representation of stability using circles, and what is the potentially unstable regions, what are the stable regions, how to determine the potentially unstable regions, and how by adding resistances in series or shunt we can convert a potentially unstable system to an unconditionally stable system. Thank you.